Hi, Aaron. How are you?
Good, how about you?
Doing good, thank you. I can show you guys and myself, but today. Hi, Levi. How are you?
Hello, good, how are you?
Very good, thank you.
Four of them. You got 4 scripts today? Holy buckets. That is a payday right there.
What? How you express your emotions?
I like getting scripts. You don't like getting scripts?
Oh, I do not like getting scripts.
Why not?
Writing is more pleasant than to reading that someone else has written. It is a little easier to write compared to read.
Not if they do it correctly. If they
How do you know that
comment
how do you know that it does correctly? You need to have a healthy suspicion to anything you see.
I guess I assume that your scripts are accurate enough, and if you find that you made a mistake, you would tell us.
Well, thank you. It's very pleasant for me, but. So what do we do with this 4 scripts? How do you? What is your vision of our goals? Or just general navigation, general direction?
Compute observables?
Very good. I cannot argue. So, which kind of observables? Why we are not happy with things that we were doing before? Yes, but we are not. Why do not we finish the course right now? Why do not we, or at least jump to another chapter? Why we are still dealing with time dependent? What is not yet resolved?
Don't have directionality in time. Looks like they don't relax.
Okay, but it is phenomenological, like because you are so educated and or you have intuition, you know that everything should relax. You expect that it will be shown in the class. But how do we come to this idea? What is missing? Like, are we still staying within standard old good quantum mechanics, or we want to jump into statistical averaging over ensemble? We're not going to touch statistical mechanics. It is a completely different area, but we realize that there are no isolated molecules, or they are very rare. So we need to take into account that if we do real, true, if you want to describe actual phenomena in nature, we need to take into account that there is a distribution of many copies of the system, and they have little different properties. Would you agree? Okay, so how do we do it?
Set up different initial conditions, and then see how your approach works for each one, and then extract the total.
Very good. So distribution, Levi suggested to have the same model and provide distribution of initial conditions, and then add all of them together and see what happens? What is the another approach? If we have the same initial condition, what can be different? Huh?
The time at which it interacts with the thing that makes it.
Oh, so like when you see lightning and thunderstorm, you observe lightning earlier than the sound of thunderstorm because your eyes are closer to the object than your ears. So you're suggesting that some molecules will be closer to the laser than another one, and because of the it takes different time for light to arrive to them, they will be at.
That would be the Doppler.
So okay, well, this may be not completely wrong, but we do not consider it as a leading effect. What else?
Sound travels slower than light.
Yeah, it is for the joke about sound, but.
Oh.
Would it be the interaction with the molecule with the external? So you have your molecule, and if it was nothing.
Show it to the camera. What you are showing is correct.
So if you have nothing interacting with it, then it would stay at that quantum state. The more interaction you have, the faster it should lose that quantum state.
Okay, so when you model by computational chemistry some metal-organic complexes, and you are modeling solvents with continuum, but in reality, some molecules may have 10 solvent molecules in the near shell, and another molecule can have 11. And they may come on the different orientation because of thermal motion. So different copies of the same objects are not identical. Because of some fluctuations of the environment, there is a so-called disorder. Any objections? Okay, how do we simplify it to the critically simple modeling? Like if we are working with two-level system, we neglect everything else. But we want to tell that each system is a little bit different. What would they differ with? Yes. So we will have disorder in their energy. We will have one system with a little higher energy, another a little lower energy. And then when we add all of them together, we expect to have some consequences. And as Aaron has suggested, the consequence will be that something will relax. This is not the whole story. It's just like lightly opening the door. There will be much more effects, but this is a first effect that contributes to relaxational phenomena. Hi, Diane, how are you? What is disorder?
The lack of order.
That's a brilliant answer right there.
Entropy.
Okay.
In terms of physical.
Yes, but if we have an ensemble of two-level systems that we describe only by the energies of the transition, how would we project your definition of disorder to this ensemble?
So we have to calculate the probability of each transition.
No. There is one system isolated, another system isolated, another system isolated, but we tell that system is disordered.
System is each one is disordered?
That each of the systems experiences different environment.
Well, you have to calculate the microstates.
We are not going to calculate. We are just making hypotheses. Otherwise, it will be too complicated.
We got to define the microstates or the system.
What are the microstates?
Also available. System is in ground state or it's in the excited state.
One two-level system or all ensemble?
Well, for the ensemble, you have to calculate based on the microstates available for each system.
Mm-hmm. But if system has only two states,
then okay, so it has two microstates. Yes.
Mm-hmm. can we assume that each replica, each copy of the system will have the same energy? If it experiences like heat, flood, vibrations, if there are
in
like,
equilibrium.
but if we suddenly freeze them and look what is the energy of each system, like molecule or quantum dot, homo-lumo gap of the quantum dots at finite temperature. We have like million of quantum dots. Each of them differently interact with its environment.
Okay.
And there is a contribution from like nuclear motion, from solvent, and this is random. At one point, it will be more interaction and another less, and these interactions will contribute to gap.
That's right.
But it will contribute differently.
Fluctuations.
Yes. So at one system, it will be one value of the gap. For another copy, it will be a little bit another one. And then we can tell what is the width, what is the maximal difference of this distribution in energies.
Didn't Patrick do some kind of calculations like that?
No.
Or he'll
We all should do calculations like that in few minutes. So, any objections about the idea? So,
What's the idea?
idea, what you've told to us, or what you agreed in public. And the consequence, if you...
Introducing fluctuation and all?
Yes, and if it is frozen fluctuation, like if everything fluctuates, you know, like kids have game freeze. You know, like everyone jumps, dances, and suddenly someone tells freeze. And then there will be different, everyone will be in a different posture. Same for the like molecules. Because of thermal fluctuations, they all take different shapes and different amount of interaction. And if they suddenly freeze, we will realize that each molecule has slightly different gap. And now we are going to watch the consequences.
Is it same that we read something in statistical formula? If we consider the canonical ensemble, still there have some fluctuation in all microstate.
It is related, but now we are going to project this feature, this property, onto time dependence. So we are going to watch or to model the, well, there are not too many observables for two-level systems. One can look on population, and one can look on the pseudo-spin projections, which has different meanings for NMR and optics, but mathematically it is the same, like 3 projections of this quasi-spin. And we are going to see how they are affected by an average over ensemble. Good? This will be illustrated in 2 physical phenomena. One, free induction decay, and second, photon echo. I'm not sure that remaining time will be sufficient for both, but it is an ambitious goal. So if we keep pursuing our old code with wave function, this becomes not comfortable. I wouldn't say impossible, but not comfortable. The framework of density metrics is more appropriate for averaging over an ensemble and relaxational phenomena in general. Therefore, we are going to do the same thing as we did before, but with density metrics. I did distribute 4 codes, and we can you can help me in choosing. We can take different strategies. So the codes are stages. I was writing the first code, then making some adds on, then second one, then third one, and fourth. We can take just one and comment out all novelties, and then it will be easier. Or we can just run them one after another and just skim through the basic principles.
Skim through the basic principles.
Okay, I like it, and then we have chance to come over everything.
And then there's not a chance for error.
There is always
No, like we don't have to comment stuff out. So we might
There-
comment.
The chance for additional error is reduced. But maybe there are like 1,000 errors already introduced to the code.
What code is the finished?
So the
Okay, which is the final statement?
please name the code that are distributed.
Delay, T, oh yeah.
Delay, decay. What else?
No, decay, P echo, false, RDM.
RDM is the first one, and echo is the last one.
The last one doesn't work.
It does work on mine, but let's start from the first one. So the first code, RDM, does absolutely the same thing as we did a week ago in this class, but all story is recast in the language of density matrix. The object that you were so happy to do quiz about. Let me bring it up to the screen. Okay, and how do I change the font? Is this one good enough for everyone to see? So the first code, RDM, if you were able to run it, then you do not need my comments. Okay, do you recognize this image? So we are considering a sequence of pi pulses that induce complete transition from ground to excited or excited to ground. So this blue and red lines correspond to occupation of ground and excited, and the dashed lines correspond to what? Sx, Sy, to the magnetization or polarization, time-dependent expectation of the transition dipole. But we have seen it last time, right? It is what we did in the lab. But the code is recast in the terms of density matrix, so it has 4 elements instead of 2. But we want to write it down in form of the vector. And here we take the symmetric form, what Levi was asking about on the lecture. Instead of grouping diagonal and off diagonal, we are doing sequence row 1, 1, row 1, 2, row 2, 1, row 2, 2. And then we define the constants which are the same constants of the optical pulse and energies. But then instead of formulating the Hamiltonian, we are formulating the Liouville superoperator. So how many? Okay, there are 2 types of terms. One that contributes free accumulation of phase because of difference in the energy. And here it is set up with the variable offset, which shows how far the energy of this 2-level system is away from the frequency of the incident light. We will need it later because we are going to add together systems with different value of this offset. And another term is with Rabi frequency, which corresponds to rate of flipping between ground excited and also making non-zero values for off-diagonal elements of density matrix. So how many elements are 0? I agree. How many free phase accumulation? Which elements, diagonal or off-diagonal, accumulate phase? Off-diagonal, right? They are in the middle right now. And how many? Huh? Ah, okay. Okay. Thank you for the question. We will slow down a little bit. So Diane was asking a question, why the elements that stand in the center of Liouville superoperator correspond to accumulation of phase for off-diagonal elements of density matrix, right? Do I formulate a question correct? So let me scratch a couple of symbols and then we all will feel more comfortable. Maybe the question will disappear. So you have row 1, 1, row 1, 2, row 2, 1, row 2, 2. But we are saving it in a form of a column vector. Row 1, 1, row 1, 2, row 2, 1, row 2, 2. And we are telling that this element, this object, this four-dimensional object, evolves in time according to linear differential equation. There is no non-linearity. So it is proportional to the same column vector. Row 1, 1, row 1, 2, row 2, 1, row 2, 2. And then it is operate, the time propagation needs 4 coefficients to find how the change in time of the row 1, 1 element will be composed as a linear combination of other things, right? And if you do the same for each of them, it will be matrix 4 by 4, total of 16 elements. But because of this definition, we call this row 1, 2, and row 2, 1 off-diagonal elements. They are sitting here and there. And to focus on their time evolution, we are looking in the center of this matrix. Yeah, so it will be plus I delta minus I delta.
In class we had the rows in a different order.
Yes. Make sense? Okay. And then after we, do you need more comments or it is clear for the rest of the code? Should I quickly? Okay. So then at each time step, we can propagate the density matrix in vector form by applying this Liouville superoperator in the power of exponential, yes? Okay. So if the argument is a matrix, then the result of XPM is unitary matrix plus matrix first power Taylor expansion. Yes, yes. So whatever we are seeing highlighted is the infinitesimal evolution of density operator for time d tau, but this is repeated in a cycle, in a loop over time steps. So we basically repeating this operation again and again as many times as we need. And as we go, we accumulate the trajectory of the density matrix in a special variable. And then we can just plot it and see how it looks like. And if needed, we can also convert it into the observables, projections of the pseudo-spin operator. All clear with this one? So if needed, you will be able to recode it from scratch. Well, maybe with a little longer time, but in principle, there is nothing. And here we have an infinite sequence of pulses where infinity equals 15, where each of pulses is Gaussian profile times cosine omega t. But since we are in the rotating frame, we are removing quick oscillations. And we have only this variable f capital, which stands for time-dependent envelope, which like bigger, smaller, with Gaussian functions. Okay? So if we look at the figure once again, here this blackish things are external field with envelope, and you see they are very dense, almost indistinguishable, fast oscillations. And the colored lines are solutions. Good? Let's go to what is the next code?
Pulse or decay?
Pulse. Okay, so let's see if we can run it.
Four instead of root? Four ensemble equals?
It should be, but we do not need it. Let me comment. Okay, I commented the line 35 and uncommented the line 34. Were you able to get the figure like this one? So how do we interpret it? What? Well, let me show the only thing that was made here, and then we will interpret it together. So here, comparing to previous code, all except the first pulse are removed. So it's only one pulse. And here its intensity, the strength of electric field, is divided by 2. So if it was pulse area is reduced 2 times. Okay? So you see it. What are the consequences? To make it work, or just intellectually explain what is the difference from previous?
To make it work, uncommon what?
Lines 34 and 35. uncomment line 34 and comment line 35. So we do have about 5 lines. What are their interpretation? Levi, what is the blue line here?
Ground state population.
Okay. Brendan, what is the red line here?
I disagree with Levi. Oh yeah, that is the ground state. Yeah.
Wait.
One starts
Blue
off.
is
Blue is ground state. Yeah.
and red.
And then red is excited state.
Okay. Jabet, what is the dashed line?
The orange one.
Uh-huh. Just guess.
Is a probability of formation.
Yeah, it is off-diagonal element of density matrix. And here is imaginary part, because it is imaginary and we want to plot it. Aaron, what is the purple dot dashes?
The other diagonal element?
Yep. What is the red? Okay. So what is the observation?
I missed why the blue line is the ground state and the
The ground state starts with population 1.
oh the ground state. Oh,
It all starts with ground state.
okay.
That got me for a second. Didn't get Levi.
Okay, now everyone is here. The question disappeared. You do not need to discuss it anymore.
The question was answered by
Okay, very good. So, but what are the observations? How does pi over 2 pulse differ from pi pulse?
It's not really a conversion.
Huh?
It does not do a full observation inversion. It only does by half.
So, yeah, inversion is 50%. What does pi over 2 pulse makes to off-diagonal elements?
Oh, same.
But let's rerun the code once again for the pi pulse. In this order, I'm going to line 53 and just remove divide by 2. Remove, save, and rerun. So let me repeat the question to Levi, well, to everyone, but Levi started already discussing. What are the difference to off-diagonal elements of density matrix by pi over 2 pulse compared to pi pulse?
They don't go back down to 0.
Yes, so they stay at finite values. Very good.
Because the off-diagonal elements of the density matrix is the root to go from 1, 1 to 2, 2.
If we
You can't go directly from 1, 1 to 2, 2. You have to go through the...
yes, we can visualize it by motion on the sphere, and it goes like first it goes to the full value of the off diagonal, and then it goes to the full value of the diagonal, right? And if we do pi over 2 pulse, then we stop in the middle.
So why does the full value of the off-diagonal only go to half?
I am speechless because I do not have intuitive answer, but a silly answer that you probably will not buy. If you just write an equation and set up right initial condition, then it comes out from the solution. But Well, if you look for projections of spin, then all of them will, and you set h bar equals 1, then all three projections will change from 0 to 0.5, from 0 to half. Also, the ones that relate to population also, SZ will change from -1/2 to +1/2. So for observables, it looks more natural, but here we directly follow the technical details. More questions for for this code.
Is there a reason there's like a lag between the diagonal and non-diagonal elements? Like if you look at the image, like, it looks like there's like a drop-back phase factor.
Yes, yes, and it is our equation of motion for density method dictates it. So first, like if you have, let's go to the Liouville operator that we already discussed. So the accumulation of non-zero values in the diagonal elements appears only if you have something in the off-diagonal elements. And accumulation of the non-zero values in the off-diagonal occurs only if you have something in diagonal. So they are diagonal and off-diagonal group of elements are conjugated to each other. Therefore, there is a phase shift.
Is that phase shift just the offsets that we have? Or is it
Well, if we take a solution for constant CW irradiation, then both diagonal and off-diagonal elements will oscillate with Rabi frequency, but they will be shifted by pi over 2 by phase. Okay. Are we done with this code? Okay, and let me offer you one more little experiment.
Can you just show row? Can you just type row and bottom?
Yes, you can show. You can do it as well.
I haven't changed.
But
RH with big capital RH. Okay. So that's not the off-diagonal elements we're talking about.
it is the off-diagonal elements we are talking about. Right now, this row that you requested to show shows zeros in 1, 1, 1, 2, 2, 1, and has 1 in the last element, in the 2, 2 element. So at the end of the pi pulse, only excited state is populated and the rest elements are zeros.
Right.
Well, numerically zeros.
Yes. Even off-diagonal elements also be zero?
They are zero. See, they are like 10 to the minus 3. But we have introduced the offset. It is not exact resonance here.
Oh.
So if you type offset, it will be some value. And through like several thousand steps, the results accumulate difference. But we do it intentionally. Right now, exactly, you're asking this question in the very right time. So we can redo this calculation for pi over 2 pulse, but let's manually change the value of the offset, which is in the line 34. Right now it is 10 to the minus 4. Let's do it like maybe 1%, which will be like 1% error mismatch between frequency of light and frequency of the system. So I'm going to save, rerun, and see what happens. What do you see? So if we look shortly after the pulse, then the result will be the same as for resonance condition. So the diagonal elements, occupations of ground and excited, come very close to 50%. And the off-diagonal elements, imaginary parts, come close to plus 0.5 and minus 0.5. But then, due to this offset, due to their phase accumulation, there appears additional evolution, additional motion. And the amount of this motion, of these oscillations, will be different based on the value of the offset. So right now, we set up the offset of 1%. What if we do like 1 over 1,000? What do you see? So it is very close to resonance condition, but still the values for off-diagonal element are not steady. They're changing in time. Less, but still changing. Okay, we are done with this code, and now let me invite you to use the code named decay. So what are we going to do here, and what is the goal? Let's assume that we do have ensemble of systems, each of which has different value of this offset. And we want to add together observables, computed for each of those, and show what we measure in reality on an experiment that consists of ensemble, of infinite number or very large Avogadro number of these systems. Today, our Avogadro number will be equal to 40. Well, otherwise it will be a little too long. So let's, the code runs the dynamics again and again for each value of the offset. Scratch something. Let's consider that we do have systems 1, 2, 3, 4, and so forth, that they differ a little bit from the exact resonance condition. So if the energy of the photon is h bar omega capital, then we will have this E12 for system number 1, E12 for system number 2, E12 for system number 3, and so forth. E12 for system number n. So some of them will be a little higher in energy, some of them will be a little lower. And then we are going to compute the time evolution for each of those. Since our driving field is infinitely powerful, we're not considering how many quanta are here. It is classical field that will equally drive all of the molecules in the ensemble. But each of the molecules will evolve in time a little bit different. So there will be like offset parameter for each of them. For some of them it will be negative, for some positive. And after adding together the dynamics with different offsets, we will see something interesting. So the code the code is the code has an additional loop, and this loop goes over ensemble. So we set our Avogadro number equals 40, and then we are setting up that the value of the offset will be subsequently increasing for each representative of the ensemble. I just didn't have enough creativity to call variable by other name. So ensemble counts from like 1 to 40, each state. And then this value of set goes from disorder over 2 from minus disorder over 2 to plus disorder over 2. So we can tell how much energies of the systems are different. For example, this value of disorder can be made equal to KT, very roughly, telling that some systems are higher, some are lower. But we are not touching microscopical background. We are just using it as a parameter. So how far energy of the individual molecule gap may differ from the average value. And then after we define the value of the offset energy, we are running the trajectory again. And at the end of this trajectory, we are adding together density matrices computed for each of the system. And then divide by number of these states in the ensemble. Make sense? Now let's run and see what happens. So while it is running, it reports which representative of the ensemble we are dealing with, so that we do not feel lost and just see the level of a progress. So it's like 6 out of 40.
So this may be a stupid question, but
there are no stupid questions. There are stupid answers, and I can prove it to you.
But wouldn't our answer for if you go to the resonance and then you go to the next nearest up and down, would they be connected by negative signs?
They will accumulate phase in opposite directions. But I was also thinking about it, like, can we get the final answer without making like 40 or 1,000 members of an ensemble? Can we take an average member of an ensemble a little bit offset to the plus and a little offset to the minus? No. One needs continuous distribution. So we are doing cheesy, well, not cheesy, but approximate modeling of continuous distribution with a large number, where large equals 40. Today in this class or for some other reason? You are very patient. But if you recode it in Fortran and submit to like a queue to the cluster, then you can do a million and do this very quick. It's just doing proof of concept with low performance equipment. So when I was debugging this stuff, I requested it to plot the intermediate trajectories all together so that they will populate the image and show in several trajectories at once. So it will be a big mess after it is done. But look at the figure. Do not look at the answer.
Oh.
So how does it, is it similar or different from what we had for individual system? So there is a stream of lines for occupation of ground. There is a stream of line for occupation of the excited. And all these dashes and dot dashes represent the off-diagonal elements for different values of offset. So you see, some of them do not change in time and stay at the value 0.5. Some of them are changing quicker, some of them changing slower, but it is a swarm of all of them. So if we add together value of density matrix of each representative of ensemble at each point of time, then you see that for the off-diagonal elements there will be destructive interference. So this fat, thick dashes is what comes out after the average over an ensemble. And if you will look longer, it will show some oscillations, but they will be decaying. So how do you interpret it? What do you think? Yeah?
Or the occupation.
So occupations are not affected much.
Occupations are not affected.
But off-diagonal elements are affected. So where off-diagonal elements are important for in terms of observables? If it is spin, then it is like magnetization. If it is optics, then it is polarization, transition polarization. So the magnetization or polarization will decay just as a consequence of the distribution over an ensemble. So let's, any questions to this figure?
Does the average of the off-diagonal elements tend to go to 0?
Yes, yes.
And that's because your phase, well,
Because some of them go with positive phase, some with negative, and then they cancel. This effect is referred with the in a terminology with the word free induction decay. Maybe Brendan has heard about it and can even give a comment.
Yep. So when you excite the, so if you excite the system in NMR and you let it decay, it releases energy as it decays, and then the waveform of the amount of energy released before you transform it to break down into individual waves is actually decaying in time.
Mm-hmm. But you approve that it decays.
Yeah.
Okay, good.
It does decay.
It does decay. Good.
Yeah. But when you do the individual waves,
Well, right now we are having too simple system for such analysis. Okay, how can we visualize this effect to better form? So I'm removing this halt stop commands in lines 118, 119. And actually, I do not need to rerun. I can just copy paste these lines and paste them into the command line. Hold off. What do we see? So we see a sphere that is used just for scale, and then there is a one line that goes from the North Pole to the equator and then does something else, penetrating inside the sphere. So let me bring your attention to the figure. You see what is going on? Let me bring your attention to the figure on the here. What do you see?
I see this plotting dots on the line.
Yes.
Is the line going inside the sphere or is it still on the...
It is inside the sphere.
Okay, because you can't read that it could be on the outside, but it's just...
But if you do the same thing for at your computer, you can click. Let's wait until it is done and no. It is still a free induction decay.
So that's just saying that your average is going down since now
Yes.
the phases are canceling.
Yes. So the length of the angular momentum vector changes from h bar over 2 to 0. So this illustrates how the value of quantum changes. But it is a provocative statement. As a result of averaging and destructive interference, the magnetization disappears.
It doesn't go to zero?
Yes,
It
yes.
still hits some value.
Well, it oscillates near 0 and then it decays completely to 0.
So how did you get the dots on the line? You just copied
I copied the lines from 136 to 140 and pasted it into the command line. And Diane, if you want to just prove to yourself that you can, that it goes inside, you can click the symbol of curly thing and rotate the image a little bit. And at a specific angle, you will see that the line comes inside. Okay? So, and let's quickly run the last code, p echo, but we probably will not have time to discuss it in detail. So, what does the code p echo does? It also has an average over the same ensemble, but we are submitting a second pulse. So after the length of the block vector magnetization becomes 0, we wait long time and then hit each system in the ensemble with a pi pulse that should flip it from ground to excited if it will be there, but it is somewhere in the middle. And then we observe what are the consequences. Bless you, Gesundheit.
Thank you.
So let me focus it on your images, because the recording will go off automatically at about 7 p.m. So I invite you to run the P echo code, and then we will discuss what is going on. Did you launch the P echo?
I got it.
Oh, you got it?
Yeah.
Anyone else?
Brandon has it. Aaron has it.
Uh-huh.
My computer must be faster than yours.
Yes, I can believe it. And your computer may have much more free memory.
Yeah.
When there is a very low amount of memory, the disk space is used as a replacement of, like, RAM and disk are used to replace each other, and it slows down everything. Javed, did you got the results of P echo?
You must be swapping too.
I only have 40 gigabytes of free data on my hard drive. Yeah, but you're saying if your hard drive is completely full, then
Or maybe my excuse is that the same facility is used for video processing.
that is true. And online and all sorts of stuff.
You also have MATLAB there, right?
Huh?
You, that runs
It was working well, but all equipment on the conferences started to use HDMI, and Air didn't have the HDMI port. So it was working good, but obsolete compared to other.
And didn't she drop it?
Probably a few times.
Because I know like the screen was.
It's a main reason to have the Mac with aluminum case, so that if you sit on it, it lives longer. Because if you sit on a plastic computer, you
But
can.
then it's bent to stay, because my old laptop I had, and I dropped it, and then it was terrible.
I got my phone once
Intentionally?
Well, if I don't drop it all week, then
I thought phones,
So
like, they're more stable. I thought they, oh wait, no, that's the same brand. They have like Gorilla Glue.
my iPhone 7 is probably using that.
Oh. Is that the one that is not reusable? No. Like if something goes wrong.
You are like that, aren't they?
No, like if your screen goes, you get a new screen.
okay, so do you have the figure like the one on the big screen?
I do.
So let's go ahead and interpret it. So let's go with the easier thing in the same order as we did first time. Diane, what is the red? Oh, sorry, the black. Dark black.
The pulse.
Yes. So how many pulses?
2.
What is the difference?
It's looks like it's 2 pi and a 5 pulse. Pi over 2 and a 5 pulse.
Okay. Aaron? So what happens to the dashed, thick dashed lines?
They decay up until the second pulse, and then it looks like it starts to grow again in intensity after the second pulse.
So when does the dashed line reaches its maximum? When does dashed line reaches its maximum? How do you observe it? We do not have video anymore. I cannot show you faces.
Oh no. Shock. That's the worst thing ever happened.
No, well.
Let's go riot. But not in the street because we can get ran over.
Well, they disconnect us. We have only limited time. But anyway, Levi?
Yes.
When does dashed line reaches its maximum?
I would say it reaches maximum at 2 points at the first half of pi pulse.
Okay.
And then after it, the phases come back to phase because they're out of phase, and then they rephase, and then they continue to dephase.
Okay. So if you measure the time interval between pi over 2 and pi pulse, how would this interval correspond to the time when the...
I believe they should be the same.
Perfect. Then you can get a certificate of an expert in photon echo.
I don't know if that's the case.
It is the case. So I think it is almost enough for... Well, let me add a comment, and then we will be done. So when the ensemble of systems is polarized at most, if upon average the polarization is still big, then the system as a whole has much higher probability to interact with light. And there is a higher probability that photons will, if we are talking about optics, photons will emit. So there is a higher probability of spontaneous emission. So we do have this simple calculation, but in addition, there are hypothetical logical connections. If we agree with a hypothesis that strongly polarized system interact with light better, then if the system will come to a big polarization spontaneously after some time, then it will have much higher probability to participate in spontaneous emission event. Objections? This is the hardest logical point I refuse to agree.
So you're saying it is highly polarized, or if the phases are off, right?
Yes.
It's higher probability to emit a photon?
Yes.
If it's in the excited state.
It is in a each of the individual molecules is in the 50-50 superposition between ground and excited. But since they are a little bit different, they have chance to be in different phases. But when they are rephasing and their off-diagonal projections interfere constructively, then this bigger system, an ensemble, has much higher chances to participate in spontaneous light emission. And this logical connection has a proof on experiment. So if you prepare this setup, it means that you are sending 2 laser pulses at time 0 after certain delay, and then you wait equal amount of time without touching the system, without applying any perturbation. And then suddenly system flashes. The system, this ensemble of molecules, spontaneously emits a lot of light at a certain time. So
is that supposed to be white light? I mean, which are all one?
No, it is. It has a central frequency, and if you, I probably didn't highlight it, but our dispersion, better word, maximal offset, disorder of systems, is maximal offset, maximal disorder is taken like about 1% of the frequency. So it's still very close to resonance, but it is sufficient to induce this effect. So the definition of photon echo effect is like what is common life echo. When you are traveling in mountains, you shout and then you wait some time, and then you hear something back. And here it goes the same way. You send some energy to the system, and then you do not touch it for a period of time, and suddenly it emits light. Therefore, the word echo is used.
So can you do this? Can you have a half high pulse, and then have another one and have a second echo?
Yes. You have an affinity to nonlinear optics and femtosecond spectroscopy based on this question. There is a very big community that ask questions like this and try to prove them experimentally or theoretically. Okay, I do not have anything in the program. Let's meet tomorrow at noon for continuing the same stories, but more from the pen and paper theoretical descriptions. Are there any questions?
Now, move it with your mouse. Okay. Now,
You gotta hold it while you move it.
Oh, no, I was talking to him.
Oh, you're just very.
His is dipped, and I was confused.
I didn't talk to Sergey.
But I was hoping I'd have like a 3D so you can get better.
Oh, I see. Okay.
So hopefully you made a better resolution that way. You know, it's locked it on the TV.
Can I go, or there are some questions to me?
No, I'm good.
No, I just have to stay with my
Good,
drive
good.
and-
Okay.
Have a good night.
There's
You
something
too.
with my